From the Library of Congress in Washington, D.C.
Good morning. I'm Stephanie Marcus from the library's Science, Technology, and Business Division. I'm really excited to welcome you to the first lecture of our 2017 series. We'll have 8 more, and this is the 11th year of our collaboration with NASA Goddard. So we're going strong, and as you can imagine, we will never run out of topics. Our speaker today is astrophysicist Julie McHenry, and she is from Ireland. She was named Fermi Project Scientist in 2009 and works with all elements of the mission. Before that, she was the analysis coordinator on the Large Area Telescope, which is Fermi's primary science instrument. She was named one of Fermi's deputy project scientists in 2005. Along with her work at NASA, she has been an adjunct professor of physics at the University of Maryland College Park since 2009. So she's a very busy lady. Dr. McHenry has touched down in many places during her academic career. She's started off with a degree in physics with astrophysics from the University of Manchester, and then received her PhD from the University College Dublin. She did postgraduate work in Dublin, followed by the University of Utah, that was quite a distance away, and the University of Wisconsin-Madison, and was a Fermi research scientist at the University of Maryland, Baltimore County. We're really excited to have Julie McHenry land at the Library of Congress today to take us on a journey into the extreme universe. Please help me welcome her.
Thank you very much for that nice introduction. It's really a pleasure to be here. I would first like to say that your buildings are much nicer than our buildings at Goddard Space Flight Center. I think it's 50s and 60s architecture versus earlier. So what I would like to talk about today is a snapshot of some of the results from the Fermi Gamma Ray Space Telescope that I think are exciting. I'm not going to try and cover everything because you don't want to be here for 4 or 5 hours. But I do think that in the last 10 years, we've opened up an entirely new way to look at the universe. We found exciting new things. We've answered questions that we have, but we've also, more importantly, opened new questions. What you see on the image there is the map of the gamma ray sky with an artist's sketch of the observatory. The main instrument, the Large Area Telescope, is actually that square box on the top. We're very much not a traditional telescope. So let me begin. If you go out to the sky at night and you look up, you'll see stars. At the right time of the month, you'll see the moon. If you know where to look, you can see planets slowly moving through the sky. And if you're in a dark enough place, you'll see the faint glow of our Milky Way galaxy. But if you had gamma ray vision and you stood on the ground and looked up, you'd see nothing, because gamma rays don't get through our atmosphere. But if you could propel yourself above our atmosphere and look at the sky with gamma ray eyes, you would see a drastically different place. The Milky Way, which in optical is faint and dim, a small glow, in gamma rays is blazingly bright. More than 85% of the gamma rays that we see come from the Milky Way. They're produced when particles moving at close to the speed of light smash into molecules of gas and light photons in our galaxy, producing this enormously bright glow. This image of the sky is in galactic coordinates, so what you're seeing is the very bright Milky Way galaxy across the center. And I've scaled this image so that it doesn't overwhelm everything else that you see. It's very, very different. If you continued to look at the gamma ray sky, you'd notice that the moon is brighter than the sun, and neither of them are really very bright at all. In addition to the radiation, the gamma rays that we see from our galaxy, you'll also see many point sources, individual sources of gamma rays. So one example that I'll talk about in a little more detail are pulsars. These are rapidly spinning neutron stars with enormous magnetic and electric fields that accelerate particles to extremely high energy and produce bursts of radiation that rhythmically are beamed towards us. We also see a phenomenon known as blazars. This is the most populous source in the gamma ray sky. So again, if you're looking at the sky in optical wavelengths, the kind of astronomy that we've been doing since the time of the Babylonians, most of the things that you see are stars and galaxies. In gamma rays, most of the things that we see are things known as an active galaxy, where you have a supermassive black hole at the center of the galaxy. And we're looking at that subset of objects where a jet of particles moving close to the speed of light is pointing in our direction and beaming and focusing that radiation directly at us. We see gamma ray bursts. A gamma ray burst is the most, or at least until the LIGO discovery, one of the most energetic phenomenon in the universe. When we see a gamma ray burst, we see a small flash of gamma rays lasting from a fraction of a second to around 1,000 seconds. And what you're seeing when you see a gamma ray burst is the birth of a black hole in a very distant galaxy. And I think one of the other things that's particularly interesting about the gamma ray sky is that a lot of it is not well known. At any given moment, about a third of the things that we see in the sky do not have a confirmed origin. In some cases, it's because there's several candidate options. And in other cases, we really just don't know what the object is, except that it's producing gamma rays, so it must be exciting. I'm not at all biased. So let me tell you a little bit about what a gamma ray is. A gamma ray is the highest energy form of light. So if you're familiar with the electromagnetic spectrum, you'll know that it starts at long wavelengths and low energies at radio. As we increase the energy or shorten the wavelength, we pass through microwave and optical. And then as we increase the energies again, we get to X-ray and then to gamma ray. But what I think is worth pointing out here is this is what our eyes can see. A very, very small swath of the electromagnetic spectrum. It's very important because we all see it. But this is what Fermi can see. The amount of range of wavelengths covered by Fermi is enormously broad. So while it's all called gamma ray, that band, that part of the electromagnetic spectrum is extremely large. And why do you care about this? Well, if you think about it, if you take a photograph of your hand, you have a photograph of your hand. If you take an X-ray of your hand, you see the bones. And as you view your hand or the universe at different energies or different wavelengths, you get different information. And it's just the same in astronomy, that if we view the universe in gamma rays, we see different things, we focus on different things, we learn different things than when we make our observations with the more traditional X-ray and optical and infrared and radio wavelengths. So there's two examples on this chart. The top shows how the sun looks in different wavelengths. The sun is actually quite an important object for us. We see it all the time, but when it flares, it can briefly become an extremely bright gamma ray source. And then on the bottom, just to illustrate how things look different in different wavelengths, there are infrared to X-ray image of somebody holding an iPhone. So how do we detect gamma rays? I told you that we have a really strange telescope. There's no mirrors in gamma rays because the gamma rays will just go straight through them. What you have to think about is how gamma rays actually interact with matter. And you might have heard of Einstein's famous equation, E equals mc squared. And what this is telling us is that energy and matter are fundamentally the same thing. C is the speed of light, which is a very large number. So if you multiply mass by a very large number, it equals energy, but a very large amount of energy. And what's special about the wavelength, the energy of the gamma rays that we look at in Fermi, is that there's enough energy in each individual gamma ray to produce an electron and the antiparticle to an electron, the positron, in our detector. So we're using this phenomenon to detect our gamma rays. And we're using them because we're converting the gamma rays from energy into matter, and then we're tracking the motion of that matter in our detector. So the Large Area Telescope is this box. So what happens is a gamma ray comes in, it's minding its own business. And the remarkable thing about gamma rays is that really the universe is very transparent to gamma rays. So this gamma ray, well, I mean, that's just a line on a screen, but if it was a gamma ray, it will have gone through millions and millions of light years. It can go straight through our galaxy. But as soon as it comes close to the Earth, it's just going to go splat because the atmosphere will absorb it. If it hits our instrument first, what will happen is that the gamma ray will interact to produce an electron and the antiparticle to the electron, the proton, indicated in those purple lines. Our detector contains instrumentation that can precisely measure the position of the electron and positron. So we measure the tracks of the electron and positron. And by reconstructing where those tracks came from, we can figure out where the gamma ray turned into matter and where it must have come from. At the bottom of our detector, we have a material known as a scintillator. A scintillator produces an amount of light that's related to the amount of energy that was deposited in it. And from that, we can measure the energy of the gamma ray. So now we know where the gamma ray came from. We know what its energy was. So we can gamma ray by gamma ray build up a picture of the gamma ray sky, one gamma ray at a time, making our gamma ray map deeper and deeper and deeper with every day that the mission continues to make observations. It's an extraordinary instrument. We have over 1 million channels of channels of electronics, but we power it, all of this, with something like a hairdryer. We're an international instrument. The instruments on Fermi were built in Japan, Sweden, Italy, France, and Germany. And the logistics of keeping all of this together while we were under a strict schedule was quite a challenge. So if I pick a few interesting fun facts. At the time that we built the Large Area Telescope, we were the largest silicon detector in the world, larger than anything that was built in the particle accelerators at CERN or Fermilab. This was enough silicon to make almost 1 million digital cameras. We collect information from 1 million different sensors, several thousand times a second. So our instrument is reading out very, very quickly all the time. It's the equivalent of an instrument that is taking an image of the sky thousands of times a second. But this is all powered by the equivalent of a hairdryer, generated with the power generated by solar energy. And interestingly, in space, our issue isn't actually our ability to generate power. We have no problem with that. We've got large solar panels. But in the vacuum of space, it's challenging to get rid of the heat. So we went to a lot of effort to design extremely power-efficient electronics. And our energy range, as I've already mentioned, is extraordinarily broad. So we take the Large Area Telescope, and here's a picture of the instrument in Phoenix, Arizona. It's the silver box on the top, and the spacecraft is just below. At that point, the solar panels hadn't yet been added. We then put the spacecraft on a rocket. So this is a picture of the spacecraft now with the solar panels installed onto the fairing in Florida. It's a very nerve-wracking moment. You spend 10 years of your life lovingly, carefully putting together precise and extremely expensive instrumentation. And then you put it on top of an enormous amount of extremely flammable fluid that is uncontrollable once ignited. And you cross your fingers and hope for the best. So many of us took this photo the night before launch because we couldn't sleep. So before I show you the next few charts, to put things into context, something that we didn't realize at the time is that there was an offset of a couple of seconds between the video feed and the audio feed of launch. So we're waiting for launch. And the countdown happens, and it's 5, 4, 3, 2, 1. And we have liftoff. And we saw nothing. And then a couple of seconds later, we saw that. And that looks quite bad. So for the briefest moment, a lot of people's hearts dropped totally into their chest. But then, of course, it was actually completely fine. And all that was really happening here is there was a larger than normal amount of water flow underneath the rocket. That you flow water underneath the rocket at launch to stop the pad from being destroyed. And we just happened to have a particularly high water supply. So that isn't smoke; it's steam. Okay, so let me tell you a bit more about what we've actually seen. So this is our sky above 1 GeV. I've shown it to you before. A GeV is 1 billion electron volts. An electron volt is a unit of energy that is about the energy of a normal optical photon. So what you're seeing here, every single gamma ray in this image has an energy that is 1 billion times the energy of the photons of light that are entering our eyes right now. But we've got a broad energy range, so I can also show you a map of our sky above 50 GeV, 50 billion electron volts. And what we see in the sky changes slightly, just as it does when you look at the sky in infrared and you look at the sky in optical. Some objects go away, some appear. But the thing that I really want you to notice are those two large lobes. I think I can do this. Large lobes above here and down here. These were completely unexpected. They're unusual because they're appearing only at the highest energies. That's telling us that they're being produced by very high energy particles. Gamma rays are produced not by heating something up to a very high energy, but by accelerating charged particles to close to the speed of light. And the more accelerated the particles get, the higher the energy of gamma rays that you produce. So if we see these large, faint lobes appearing at the highest energies, what it's telling us is that there is a population of particles, of electrons or protons, we don't know which, in our galaxy that have been accelerated to extremely high energies. These lobes are really quite extraordinary. They loom over, above and below the galactic center, extending for 25,000 light years above and 25,000 light years below the galactic plane. If your eyes were sensitive to gamma rays, the Fermi bubbles would extend over almost half of the sky. They would absolutely dominate the sky that you see at night. And we had no idea these existed until we had Fermi, an instrument that was sensitive to the photons dominantly being produced by the Fermi lobes, and with a field of view that's large enough to map them completely. If you were to turn the Fermi bubbles on their side, they would envelop us. But they don't, because they're perpendicular to the plane of our galaxy. And of course, we lie in our galaxy. So you can see the label of the sun. There's lots of things extraordinary about this. The total amount of energy in the Fermi bubbles is equal to somewhere between 1,000 and 10,000 supernovae all going off at the same time. The energies of the individual gamma rays are extraordinarily high. This, I think, is one of the most unexpected things that we could ever have found. So what do we think it is? Well, first, before I go that, let's, another couple of, this is one of the early maps that we used to find the Fermi bubbles. And there were two features. The first I've already described is that the Fermi bubbles have higher energy gamma rays than most of the rest of the emission in our galaxy. So they stand out when we make a map of higher energies. They also have sharp edges, and the sharp edges are important because the sharp edges suggest that they were produced by some transient event, that something happened that produced a shock wave that went out into the intergalactic medium, blowing up the bubbles. So now the question is, well, what could that possibly be? To think about this, you need to try and imagine where is a good place to produce a lot of energy. Well, we know that the center of our galaxy contains a supermassive black hole. It's not active at the moment, it's quiet, it's quiescent. We know it's there because we can see the pattern of the stars as they orbit the center of our galaxy. But what the Fermi bubbles are telling us is that somewhere between 1 to 3 million years ago, the center of our galaxy was not quiet. And there are two possibilities. One is that the black hole itself became active, that perhaps some stars dropped in and you had a large accretion event that produced the same jets, the relativistic jets of the particles moving close to the speed of light, beamed into a narrow jet, were produced when this accretion event happened. Or perhaps you have a large burst of stars that all form at the same time. The large stars will live a very short life and will go supernova at around the same time. And that's another way of producing an enormous burst of energy. Or perhaps we have both, that initially you have a large burst of star formation followed by accretion onto the black hole, produce a jet that then continues to power and energize the shock as it extends out. It's relatively recent. So 1 to 3 million years ago, humans were on Earth. So in astronomical terms, I mean, this happened like, just the other week. So I think it's very exciting to have concrete evidence that the center of our galaxy, the black hole at the center of our galaxy, did not behave in the recent past the way we see it now. Okay, so let me tell you a little bit about how we make observations. This is supposed to be an animation. There we go. So we've got a huge field of view. The field of view of our instrument we see about 20% of the sky at any instance. That's about what your eyes subtend. So what we do is if you imagine you're going around the Earth and you just always point yourself away from the Earth, you'd sweep out a swath of the sky that would cover about 80%. But we're not interested in seeing only 80% of the sky. We want to see the whole sky. So what we do is we tilt north for one orbit and cover the northern hemisphere. We tilt south for the second orbit to cover the southern hemisphere. And what you see in this bottom right-hand chart is the coverage of the sky over those two orbits. We see the entire sky every 3 hours. And that's particularly important because the gamma ray sky is highly variable. Gamma ray bursts are popping off. Our active galaxies are flaring, sometimes by changing their flux by a factor of 100 on timescales of hours or days. So here what I've done is taken the Fermi sky and taken the northern hemisphere and put it on the left-hand side, and the southern hemisphere and put it on the right-hand side, and the very bright galactic plane is now a little bit suppressed, so you can see the other things that are varying. Most of the things that you're seeing are active galaxies, supermassive black holes at very large distances from us, with jets, relativistic jets with particles moving close to the speed of light, pointing directly at us. You'll also notice that there seems to be a source running around. This image is this movie is made of a sequence of one-day snapshots. So this is what our sky looks like every day. The object that's running around is the sun. So we can see it. It's not, it's not that it's not there, but it's certainly not as bright as the optical sun. I mean, imagine trying to take an image of the sky when the sun is up. You certainly wouldn't see any stars. I did mention earlier that the moon is brighter than the sun, but of course on these timescales the moon is moving through this image much more quickly. So you're not seeing the moon because it's smearing across a larger number of pixels on an integration time of a day. So I'm going to switch gears a little and talk about one type of object. So if you start, the Earth is kind of small in the grand scheme of things. It's very important to us, but we're really kind of tiny. And I'm showing this just to give you a sense of the scale of size between the sun, the moon, and the Earth. And I'm telling you this because I want to give you a feel for how large the sun is. Now imagine taking the sun and compressing it to something that would fit inside DC. You'll have enormously high densities. when you compress things, you also compress the magnetic field. So you end up with a magnetic field that's more than 1 million times more intense than anything we can produce on Earth. So now you have something that's incredibly dense with an incredibly high magnetic field, and we spin it rapidly. And by rapidly, think of something like a ceiling fan. I mean, can you imagine something that is the mass of the sun, the size of DC, and spinning as rapidly as a ceiling fan? These are really extraordinary objects. So it shouldn't surprise us that this is the kind of place that gamma rays can be produced, because when we're producing gamma rays, we're looking for extremes in the cosmos. We're looking for extremes in magnetic fields, extreme energy, extreme acceleration. We don't, in general, see stars in gamma rays unless they're exploding or have exploded and are in a more energetic phase of their life. So what you're seeing here is an animation of a rotating neutron star, just to give you the sense of how you're going to see a sequence of pulses from the emission being produced at the two magnetic poles. Neutron stars are produced in stellar explosions. So you produce a neutron star by starting with a normal star. At the end of the star's life, it stops the nuclear burning. The material collapses on the center into a huge explosion, and the remnant of this is either a black hole or a neutron star. So this brings me to the very first result that we had with Fermi. So October 16th was our publication date, which means since we started operations in August, that this first result was based on our first couple of weeks of data. What you see on the left-hand side is the grayscale is a radio image of the supernova remnant CTA-1A. A supernova remnant is the outer bits of the shock that's produced when a star explodes. The blue circle is the size of the uncertainty. So we knew that there was a gamma ray source here, but we didn't know where it was better than to the size of this blue circle from 6 years of observation with the previous instrument. The red circle shows how well we could pinpoint the location of this source with Fermi after just 2 weeks of data. The red source lies right on top of an X-ray source. So it's clear at this point that the gamma ray source and the X-ray source really must be the same thing. So the gamma rays being produced, in this case, were not being produced by the supernova remnant. They were being produced by whatever that X-ray source was. But what makes this really interesting is that when we looked at the data, we realized that the pattern, the arrival time of the gamma rays was not uniform. That every 316 milliseconds, we were seeing the same patterns. So what you're seeing on here is 0 to 316 milliseconds, and then we're just repeating the same thing again. And this is telling us that for each rotation that this source is rotating at 316 milliseconds, and that the gamma rays are arriving at the same point in this rotation each time. So it's telling us that this is a pulsar. But it's not a pulsar in radio. It's not a pulsar in X-rays. This was a pulsar shining only in gamma rays. And that was telling us that we were never seeing the full sample of pulsars in our galaxy, because before Fermi, we didn't have an instrument that was able to find most of the pulsars. And they're important, because a pulsar is the end stage of a star. So if we want to understand the full life cycle of a star, you have to understand them from the birth right the way through to the death, and this is the death. So if you, this is an early degree of PowerPointmanship. So this is, we've taken a bunch of the early pulsars, manually put them onto the plot, and then add an animation that is flashing 10 times slower than the actual pulsar. But it illustrates what we have in the sky. So CTA-1 was just the first of many pulsars that are found only in gamma rays. We have over 60 that are shining only in gamma rays. About a third of the pulsars that we know of shine only in gamma rays. We've also found 60 normal pulsars, the ones that are also shining in radio. But you'll also notice on this image that there's pulsars in pink that look like they're just doing their nut. They're going very, very fast. Those are millisecond pulsars. And those are a special kind of pulsar. They're pulsars that reached the end of their lives, slowed down, then they accreted material from a companion that sped them up again until they were again turned on as pulsars. They're known as millisecond pulsars. They're very special objects, and they're very special objects because they're excellent clocks. So one of the things that Fermi's been able to do, that over half of the known millisecond pulsars have been found from Fermi searches. And what we use millisecond pulsars for is that you've got something that's spinning very, very, very regularly. So it's an excellent clock. So if you imagine you've got a very large gravitational wave coming through the galaxy that's distorting space-time, it's going to slightly move the arrival time of the radiation from these millisecond pulsars. And we can use that to chart the passage of very large gravitational waves. So with this, we can create a galaxy-sized gravitational wave detector. So this is just one example of what you can do with the millisecond pulsars. We have another mystery. So this is not gamma rays. This is an optical image of our galaxy. And the animation that I'm about to show is going to zoom in towards the center of our galaxy. So this is close to the center, so not like the Fermi bubbles. Oh, hang on, we need to actually play it. As we get closer, this animation will superimpose what we see at the galactic center. And as the animation continues, all of the known ways to produce gamma rays will be subtracted. We'll subtract the background. We'll subtract the point sources. And what you get left with is a blob about 10 degrees in size that is also unexpected. It has an unusual spectrum. And by spectrum, I mean the distribution of energies of the gamma rays. That this peaks between 1 and 5 GeV. A supernova remnant doesn't behave like that. A pulsar can, but a pulsar isn't 10 degrees in size. So this is one of the second mysteries that we have at the center of our galaxy. But the center of our galaxy is special because that's where the largest gravitational sink is. You might have heard of the mystery of dark matter, that there is a material in our galaxy, there is material in galaxy clusters beyond what we can actually see radiating. And our colleagues from particle physics tell us that the leading candidate for dark matter, because it solves one of their particle physics problems, is a new particle that when it encounters itself will produce gamma rays. Where would you expect to find the most dark matter in our galaxy? Right at the center. How would you expect it to be distributed? You'd expect it to be distributed in a blob. What would you expect the spectrum to be? You'd expect it to be peaked and have a sharp cutoff related to the size of the dark matter particle. So one exciting possibility is that what we're seeing here is a signal of dark matter in gamma rays. If we look at our neighboring galaxy at Andromeda, so this is a very recent result published earlier this year, we found the same thing in Andromeda. So what you're seeing on the left-hand side, the contour lines chart where the gas in that galaxy is. If the gamma rays in Andromeda are produced by very high energy particles smashing into gas, then the gamma rays should be following the pattern of those lines. And it is not. The gamma rays are concentrated at the center of that galaxy. So like our galaxy, Andromeda has an anomalously bright emission of gamma rays. Like our galaxy, Andromeda sees the same distribution of energies. So whatever we see in the center of our galaxy is not unique to our galaxy, but is a phenomenon that's likely present in all normal galaxies. So this is potentially very exciting, and we're still excited at the prospect of this being dark matter. But you have to always consider other possibilities. And now that we know that there's a large number of pulsars in our galaxy, it's possible that we have a large population of millisecond pulsars around the center of our galaxy. And from my perspective, it doesn't really matter which of these are correct. I think it's incredibly exciting that we have discovered that the center of our galaxy had activity several million years ago that we didn't know about, and that now the center of our galaxy contains components that we didn't know about. I'm going to switch gear completely. Everything I've spoken about so far are data from the Large Area Telescope. That's this box up at the top. But there's other instrumentation on Fermi. We have the gamma ray burst monitor. It's an array of instruments. There's 3 here, 1 here, another 3, and the same on the other side of the spacecraft. And this instrument is designed to detect flashes of gamma rays at lower energies than the main Fermi telescope, the Large Area Telescope. So what kind of things do we see? Well, a gamma ray burst, I've already mentioned, is the birth of a black hole, either because 2 neutron stars merge, or a neutron star and a black hole merge, or a large star has an extremely energetic supernova. There's an object known as a magnetar, and a magnetar is an extremely high magnetic field neutron star. And when you crack the crust and have a sudden large release of magnetic energy, you get a large burst of gamma rays. The whole star is shaking. So the gamma rays are coming out in a periodic motion. But this periodic motion isn't telling us about the rotation of the magnetar. This periodic motion is telling us about the structure and the interior of the star, just as the sound you get from a bell is determined by the material of the bell and its shape. We can use the pattern of the signal from the gamma rays from magnetars to explore the interior structure of a neutron star. We see gamma ray flashes from the sun, less now that the sun isn't active. And the topic that I want to focus on, because I thought I'd do something other than astrophysics, are thunderstorms. Because the Fermi Gamma Ray Burst Monitor sees the entire sky, most of it is the sky, but the Earth is underneath us, so we don't see the sky through the Earth, we see the Earth. And when the spacecraft is over regions of the Earth that have thunderstorm systems, we quite often see a very short, brief flash of gamma rays, lasting just milliseconds, with a very characteristic spectrum, very characteristic distribution of energies. And if you plot where you see these unusual transients in the sky, you'll find that they lie on top of regions where there were thunderstorms. This was the moment where I learned that thunderstorms happen largely over land. I think it's kind of obvious from this. But what's interesting is a handful of them show very unusual properties. So we had a situation where the spacecraft was above Egypt, and we saw one of these terrestrial gamma ray flashes of gamma rays produced in thunderstorms. But there wasn't any thunderstorms in Egypt, but there were in Tanzania. And if we look at there's 2 things I want you to look at. The first is on the left-hand side, what you're seeing here is time on the x-axis and counts, number of gamma rays on the right axis. And what we saw was a peak, and then it calmed down, and then we saw another little peak. And that's unusual. But what I really want you to look at is on the right-hand side. On the right-hand side, what you see is energy along the x-axis and number of gamma rays on the y-axis. And there's a sharp spectral feature. The energy of that bump is at 511 keV. That's exactly half the energy of an electron. What's happening here isn't that we're seeing gamma rays directly. What's happening is that positrons are directly hitting the instrument, are converting, they're encountering, so the positron is the antimatter particle to the electron. They're hitting electrons in our detector, and they're doing the opposite of the pair conversion that I spoke about before. So E still equals mc squared, but in this case, we're turning the matter back into gamma rays, and then we're detecting those gamma rays in the instrument. This also was a surprise. So you go back to the drawing board and you think, well, you know, what's going on here? So this image shows a thunderstorm on Earth. The moon is there just for context. And in the thunderstorm, The pink are gamma rays. So what you have is an enormous amount of acceleration in the thunderstorm. The thunderstorm is accelerating particles. The particles are producing gamma rays in the atmosphere. But the accelerated particles, when particles move in a magnetic field, they have to follow the magnetic field line. So the charged particles are in yellow, can't spray out in all directions. They're following the magnetic field line. So if we move on to the next animation, now you can start to get a sense of what happened. The thunderstorm happened in Tanzania. You've got a pulse of charged particles. This is a pulse of electrons and positrons that are traveling along the magnetic field line for thousands of miles, hitting our spacecraft. Then they're continuing along the magnetic field line until they reach the conjugate point, at which they bounce and come back and hit the spacecraft again. So this is the same kind of phenomenon that keeps charged particles in the Van Allen belt. I find it quite amazing to realize that even if you're thousands of miles away from something, that a thunderstorm is affecting us by sending antimatter directly to us from thousands of miles away. So I'm almost finished. I'm not going to talk about all the other things that we do, but we have done and continue to do extraordinary things. So what I'm showing here, starting on the bottom left, close to us, and going up to the top right, to most distant from us, are all the astrophysical topics that Fermi has produced a press release on. Everything in yellow are things that were not known as gamma ray emitters before the launch of Fermi. So we haven't just seen more gamma ray sources. We haven't just measured known gamma ray sources more precisely. We have understood the energetic universe in a way that we had no idea before the launch of Fermi. This has opened our eyes in whole new ways. And I am pleased that we were able to address the questions that we said we would address when we launched the instrument. But I think as a scientist, what makes me most excited about Fermi is that we've raised new questions. We know the Fermi bubbles exist, but we don't know yet precisely what causes them. We know that we've got an excess of gamma rays in our galactic center, but we don't know what that excess is. I could have given this talk and covered an completely different range of topics, and I sometimes do. And I think they would have been, at least to me, just as compelling as what I've described to you here. So I think my summary is to say that, really, there's much more to the universe than we can see with our eyes. This is true on Earth just as much as it's true in the cosmos. My day job is extremely exciting because our observatory is constantly scanning the entire sky, and the sky is constantly changing, so there's always something new to find. I talked about two unexpected and different features in our galaxy. We have the huge lobes that are tens of thousands of light years in size, and then we have this unexpected blob right in the center of our galaxy, both of which have potentially extremely exciting explanations. The first is that the galactic center was not as calm and quiet in the near past as it is now. And the other might be a signal of dark matter, or might be telling us about a whole population of objects close to the center of our galaxy that we didn't know about. And there's a ton of things I didn't discuss, but what can you do? Thank you.
Thank you so much. We have time for some questions, and I will ask Dr. McHenry to repeat them so everyone can hear them.
Yes. When a gamma ray is just traveling through a vacuum, it's going to stay a gamma ray. But when a gamma ray passes close to the electric field of a nucleus or to another photon, in that scenario, then you can have a physical interaction that converts the gamma ray into a matter and antimatter pair. The matter that's produced is related to the energy of the gamma ray. Electrons are light, so that's mostly what's produced, because we don't have gamma rays that are large enough to produce any other particles. So now we have two charged particles. We have an electron, which is you've probably heard of, and the positron, which is the antiparticle to the electron. The electron has a negative charge, the positron has a positive charge. The silicon in our detector produces a signal when a charged particle goes through it. So with each layer of silicon in the detector, we're pinpointing the path of that electron and positron. So if you imagine you see the electron going this way, the positron going this way, you draw a line between them, and the gamma ray then just has to come from where that line kind of averages out.
Just to follow up, has there been any other instance where we've seen that description or that model of Einstein's formula?
Yeah.
Just, matter change the energy. I mean, we know that.
Yes. So the other place where we see this quite commonly is in the detector that I've just described you here is very, very similar to the kinds of detectors that they build in the particle accelerators. And in fact, that's why this mission is a partnership between the Department of Energy and NASA, because we work with the particle physicists. So the other place where you have these kinds of detectors and you're measuring the same phenomenon is at places like the Large Hadron Collider in CERN. And in that case, they're smashing protons together, and in that collision, they're also producing high-energy gamma rays that are having exactly the same phenomenon in the detectors at CERN, that they're producing electron-positron pairs. And the physicists there can do the same thing that we do, reconstruct to figure out how energetic those individual gamma rays are.
Please repeat the question.
Sorry.
I have one. Is this mission going to continue for many, many years?
So the question is, will this mission continue? We do not have anything that is consumed on board. We have a propulsion system, and there's a requirement that if you have to have a propulsion system. If you don't have a propulsion system, you have to design your mission so that you deorbit within, I think, 15 years. Because we have a propulsion system, we're in an orbit that will remain valid for science taking until at least 2050. Our performance now, almost 10 years after launch, is actually a little bit better than it was at launch, because we've refined how we process the data. So at this point, we will continue making observations for as long as they're scientifically valuable. And every 3 years, we are reviewed, and that determines whether we continue on into the future.
So what about high-energy solar flares that you did not discuss?
Okay. High-energy solar flares are interesting for us because one of the results that I didn't have an opportunity to discuss. So here is a picture of the sun during 3 solar flares that we saw with Fermi. And what's amazing is that these images were taken by stereo. The stereo can see the back of the sun. So this is not the part of the sun that's facing the Earth. This is the part of the sun that's facing away from us. And yet, we saw a bright flash of gamma rays lasting about 2 hours, associated in time with the outbursts that you see in this movie. So what must be happening is that the sun, when it has a flare, you have it's throwing material way out into the solar system. Those particles, like I discussed with the TGF, follow the magnetic field lines long enough that the particles, the energetic particles, are now far enough away from the sun that we can actually see them directly from Earth. So this was, one of the real things that we've learned is that when the sun flares, it's kicking material very far away, and that the particles in that kicked out material are being accelerated to extremely high energies. And we wouldn't have known that if everything was coming straight for us, because we can't tell the difference between gamma rays that are produced right at the sun and produced kind of halfway to us if it's all in the line of sight. But in this particular case, it was telling us that the geometry of how the gamma rays are being produced was not what we expected.
How energetic are
The gamma rays in each of these three flares, these were very, very high energy. So these ones were actually seen by our main instrument, the Large Area Telescope, and they extended up to a few GeV. So
What's the process of the gamma rays being absorbed in our atmosphere so they don't?
the gamma rays are absorbed in our atmosphere in the same way that they're absorbed in our detector. So the gamma rays come in and they will interact with or pass close to an atomic nucleus in the atmosphere and produce the electron-positron pair. And in fact, if you look at gamma rays that are much higher in energy than the ones that we do, that process produces electrons and positrons that are themselves very energetic. And those electrons and positrons interact and produce more gamma rays. And the gamma rays interact to produce more electrons and positrons. And you've got a cascade of particles moving through the atmosphere. So before I moved to NASA and started working on Fermi, I worked on instruments on the ground that detected the particles that are produced in the shower. And if the initial gamma ray has a high enough energy, then some remnant of the gamma ray's passage through the atmosphere is still there at ground level. And what we do is measure the particles that reach the ground, and from that figure out where the gamma ray came from.
You mentioned gamma rays being created by lightning. Have you detected gamma rays coming therefore from storms on Jupiter?
We have not. We have looked.
Okay.
But if you were to scale the intensity and then move out to the distance that Jupiter is at, we wouldn't expect to see gamma rays from thunderstorms on Jupiter unless they were much, much more intense than the models predict. Yeah.
Have you seen these bubbles coming off from the center of other galaxies?
So the question is, have we seen the bubbles from other galaxies? And the answer is maybe. It's hard to see them from, we're not able to see very far away. We do see large gamma ray bubbles from Centaurus A, which is a large radio galaxy. Actually, if I go back to an image, I can show it. Because I go back to it, then I won't be able to find it. But so Centaurus A is a source that's just here. But it's not quite the same because the Centaurus A contains a currently active black hole with a relativistic jet. So it's possible that what we're seeing in Centaurus A is something that's in the process of making the bubbles. But we have not seen the gamma ray bubbles from any other galaxy that's calm and quiet. But for the same reason that we don't expect to see thunderstorms on Jupiter, if you were to take the intensity of the emission that we see from our galaxy and move it, to how dim it would look if you put it in another galaxy, in most cases it would be invisible.
Assume when gamma rays, they go at the speed of light, but if more than if they become matter, how fast do they travel?
It depends. So the question is how fast, when gamma rays convert from energy into matter, how fast do the resulting particles move? And the answer is it depends on the energy of the gamma ray. That if the gamma ray has just enough energy to produce the electron and positron, then the electron and positron will actually be at rest. If the gamma ray has more energy, then the resulting electron and positron will have more energy, and energy is directly related to how fast the particles are moving. So the speed of the electron and positron that are produced depends on the energy of the gamma ray that produced it. And in most cases, the electron and positron are themselves moving at close to the speed of light.
So if it stops, you don't see it.
If it stops, you'd probably consider it would almost be immediately absorbed. So I think you would see it, but you wouldn't measure much.
Is that everything? One
question,
more.
if I may. Doctor, you might have mentioned this. Is there a are you able to discern patterns in outbursts that would be dangerous to the Earth? Even with solar flares, with everything you discussed.
Yes. So it is certainly the case that, and when we joke about this, that a gamma ray telescope is almost like an anti-SETI, that anywhere that could produce gamma rays is going to be extremely inhospitable to life. Some of the phenomenon that I've described, if the radiation was produced by, if that same phenomenon happened close to us, it could be quite severe. So there's a couple of examples. The magnetar, which I described with the GBM. Some of those magnetars have, when the magnetic crust cracks and you have this huge release in energy, these objects are in our galaxy, and the radiation that we see on Earth can be sufficiently high that it would knock out electromagnetic communication. We haven't had one of these outbursts in about 15 years. And in the past 15 years, our electromagnetic infrastructure has greatly increased. So could we tell you that something bad was happening, you need to protect yourself? Probably not, because by the time that we see something, the bad has already happened. However, we could tell you what the problem had been. And I think that actually would be extremely important, that if our communication systems were suddenly knocked out, it would be very helpful to know that it was a natural astrophysical source that caused that.
Have you seen anything that could suggest burning all life right off the planet?
So the second example would do that. On the left-hand side is a gamma ray burst. And we see gamma ray bursts from the edge of the universe. If a gamma ray burst happened in our galaxy and the radiation was beamed towards us, it would damage life very severely. Not necessarily directly, but it would change the properties of our atmosphere sufficiently severely that if you didn't die in the immediate radiation exposure, life on Earth would be very difficult for some time afterwards. And there are some hypotheses that the age of the dinosaurs, that it is one of the candidate ways that dinosaurs stopped being around.
I hope no one has nightmares after this lecture.
Well, it has been a long time. They're not that common.
Okay, I guess that's it. Thank you so much for coming. Thank you, Dr. McHenry.
This has been a presentation of the Library of Congress. Visit us at loc.gov.